So we discussed last time about the conformal mapping. Okay. So the conformal mapping is okay. This is just I just copied from the previous lecture. Okay. So we have the two plane, right? And this is Z plane. This is zeta plane. Okay. And usually zeta plane is much simple geometry. Okay. And we would like to using the so-called conformal transformation. Okay. This is from the zeta plane and come to the Z plane or vice versa. Okay, you can also change to Z plane to here, but in this case we can switch. Okay, so Z is this is our transformation function. Okay, our mapping function, and this mapping function of zeta. Zeta is this plane. So usually zeta is a simple geometry. And then by convert through this mapping function, we would like to convert to the more complicated geometry. Okay, so we know how to write down the complex potential in this flow field. Okay, however, if you do the transformation, you understand. Okay, our Gaussian equation, according to previous. Okay, our Gaussian equation during the transformation, you have to satisfy. Okay. Your f prime should not be equal to 0, and at f prime equal to 0, okay, that's differential at the f prime, the differential derivative of f prime equal to 0 point. We call this is the critical point, and the critical point is what happened to the critical point. Okay, critical point, the flow or the geometry may not be conformal. Okay, that's and all the conformal mapping. Okay. Will be have to be spatial take care at this critical point, and later we will see that. Okay. So this is just last time we talking about mapping transformation, okay, or conformal transformation, and we mentioned about what is critical point, okay. And in this chapter we would like to using this mapping, okay. We will introduce a spatial transformation or mapping function called the Ch4 transformation. Okay, so this chapter is all talking about Ch4 transformation. Okay, and Ch4 transformation is related to the one airfoil, okay, called Ch4 airfoil. So here is a Ch4 airfoil. Okay, so this is our transformation mapping function. Okay, so Z is equal to zeta plus C squared over zeta. Okay, that's the transformation. This is called the Ch4 transformation function. And this Ch4 transformation function allows us to transform, okay, a flow over a cylinder, or okay, this kind of simple flow. We already know how to write down the complex potential for this flow in zeta plane. And through the Ch4 transformation, we can convert this flow pattern to what? To flow over airfoil. And this airfoil is a special name called Ch4 airfoil. Okay, so we would like to do this, okay, through this Ch4 transformation. And let's take a look about what's the Ch4 transformation mapping function here. Okay, so we will start from here. Okay, that's in your lecture note. In your lecture note, we will start from Ch4 transformation. This is our mapping function I just mentioned, right? Z is equal to zeta plus C squared over zeta. Okay, and C square is usually the real number. Okay. First thing is you can see if you zeta approach to infinity. Okay, this zeta and zeta go to infinity. What happened to this term here? C square is real, is a finite number divided by infinity. This term will be vanish, right? Will be disappear. So our Z will be equal to zeta, right? Z will equal to zeta. So the Z equal to zeta, that means what's physical meaning of that? When zeta approach to infinity, that means far away, right? Far away. Okay, in the flow field, far field. Okay, and in the far field, the flow field. Okay, our Z plane, zeta plane make no difference. Okay, so our velocity will be exact the same in the far field. Okay. Everything is the same because the Z is equal to eta in the far field. Okay, so this is the first point we would like to make here. Okay, And the second point is what? Since this is our transformation function, we would like to know where is the critical point for this transformation function. So this is transformation function, okay? And we take, this is transformation function. We take a derivative with respect to zeta, that df d zeta, and this f is equal to z, right? So z dz d zeta. So we take the derivative, what happened? Zeta to derivative become 1, right? And this term here become minus c squared over zeta squared, okay? And when this equal to 0, right? When it's equal to 0, we call this a critical point. However, if you take a look, when zeta, for this term here, when zeta, okay, is equal to 0, and this become infinity here. So this is a singular point, okay, singular point. A singular point, that means mathematically you cannot define. And then so a zeta equal to 0 is a singular point mathematically, okay. However, since most of the case in our physics or in our physical problem, okay, our zeta equal to 0 is always typically not inside the flow domain. It's not inside the flow domain. It will be inside the L4 here, like this, like here, okay, like here, okay, like here. This is zeta equal to 0. So flow domain is outside of flow here. Zeta is here, so it's will not influence our physical problem at all. Okay. So this point is even zeta equal to 0 is a singular. However, zeta equal to 0, okay, has no consequence because usually at this point is not inside the flow domain. Okay. And where is the critical point? If we take a look at this equal to 0, and our zeta should be equal to what? Zeta should be equal to positive c or negative c. If you substitute into this value into this derivative, it was equal to 0, right? So this is two critical points we have, okay, inside this mapping function. So these two critical points you have to special take care. Okay, later you will see when the flow approach to this two critical point, the geometry may not be conform. Okay, 我们以前讲，经过这些 critical point 的时候，我们的保角转换就不见得保角。Okay, you will see. So if you do that, if you take the positive c and then through this transformation, okay, this mapping function, z will be equal to c plus c squared over c will be equal to positive 2c. So during the transformation, this point, okay, z in zeta plane, zeta equal to c, this point will be transformed to in the z plane, z equal to 2c. And then in zeta plane at the minus c point, at this point, okay, with mapping to minus 2c point in z plane here. Okay, according to this transformation, if you apply this. Okay, so this is a two critical point for this mapping function. Okay, and okay, so once you understand this function, okay, Jacobi transformation function, we will start to discuss about, okay, what happens when we have a curve go across this critical point. Okay, so when we have a curve passing through the critical point, what happens? Okay, because we already know through a critical point, our conformal mapping may not be conform, right? If you don't understand this sentence, I would like to emphasize here. If you go back to your previous lecture, okay. If you go back to your previous lecture, 4.2, I believe. Okay. We start talking about conformal mapping, right? So here is a conformal mapping. Okay, here is the previous lecture. We're talking about the conformal mapping. So through the conformal mapping, you will have this, right? I already mentioned, okay? Our carbon equation, okay? Carbon equation in the Z plane and transpose to zeta plane, okay, should be equal to 0, and this is also equal, except at this point, right? Critical point. And also, if you check here, okay, since through the transformation, our length will be increased or decreased, right? So this is the length in zeta plane, and this is length in the Z plane, and the magnification factor is the dfdz, absolute value of dfdz, right? So this is our scaling, okay, scaling factor, okay. So if dfdz equal to 0, it means our scaling is what? Is disappear, right? Is equal to 0. So this is a very special case for. And also here, conformal mapping, when you have an argument, right? And this argument means the angle. So angle for in zeta plane and in Z plane, only the difference is what? Is dfdz argument for this angle, right? This angle minus this angle should be equal to this angle, okay? So if this, and we also mentioned is the relative angle of the shape are preserved, okay, and you can see that the beta 1 is equal to beta 2, right? I just mentioned here. However, when you have when the curve goes through a critical point, beta 1 may not be equal to beta 2 anymore. Okay, so all this is because of critical point. Okay, so you have to specially take care about the critical point. That's what I mean. So let's take a look what happens when the curve passing through the critical point. So that's this transparency we'd like to discuss. Okay. 当你这个 curve 经过一个 critical point， 它到底会怎么样去转换 ？Okay, because we know conformal mapping may not be preserved. Okay, so when the smooth curve passing through the critical point in Z plane, in zeta plane, and then what happened in the Z plane? Okay, we can take a look for this. Okay, this one. I think I can change. That will be, I think we're using this because something is missing here. Okay, so this is a critical point we just mentioned, right? In the data plane, this too is a critical point. Okay, so if you can see that. Okay, so if we have the zeta, okay, and equal to C plus rho 1 is potential IV1, okay? So that's the corresponding to the coordinate for this point, okay? This is the coordinate, any point. I would like to write down this point, the coordinate, corresponding to this point here. So this point is C, right? And the distance from here to here is rho 1, okay? So it's rho 1. The angle here is a mu1, so this is mu1. Okay, so I can write down at this occasion, okay, this point, the coordinate, by written like this. Okay, and I can also using this point, and this point to describe, okay, the coordinates for this point, and how to describe. As you can see, if you are using this as a reference point, so this point will be equal to minus C. This is minus C, right? And then from here to here is a rho 1, right? This is rho 1, rho 2, I'm sorry, rho 2. Okay, so this is rho 2, this is rho 2. And the angle here is a nu2. So this is, for the same point, I can using this reference point, C, and this reference point, minus C, and then their corresponding distance, rho 1 and rho 2, and nu1 and nu2 angle. I can written like this, okay, for any point. And then this point, okay, also through the transformation we will transform to here, for example. Okay, And then in Z-plane, okay, I also using the positive 2c and minus 2c these two as a reference point. For this point here, okay, the coordinates for this point Z will be equal to 2c plus what? This is R1, right? This is R1 times its potential I C dot 1. This is C dot 1. And also for this point here, for this coordinate, using this as reference, become minus 2c plus low 2. And this is 2, low 2 times its potential I C dot 2. So I can written like this, okay, for a generating point, okay. So I do a little bit, okay, kind of mathematics here. So through the Jacobi transformation, okay, as you can see, this is a Z. I put these 2 points, okay, and this is Jacobi transformation. And before I put these 2 points inside here, I changed this formula slightly, okay. What I did is I add or subtract 2c for these two, for both sides of the equation. So for this equation, on the left-hand side equation, I add this term here. On the right-hand side equation, I add the same term here. Okay? 所以左边跟右边我们同时加上这个项 Okay? So here, for on your right-hand side equation, you can see very easily. Okay, it become the zeta positive plus and minus c square. Okay, this is the term here. Okay, and divide by zeta. Okay, so this is will be this equation. This formula can be simplified as this. Okay. And for here, okay, as you can see, I try to understand what happens when the z minus 2c over z plus 2c, okay, for these two terms here. And this z minus 2c, according to the formula here, is what? Z minus 2c is equal to R1 EI theta. Z plus 2c is equal to R2 is potential EI theta, right? And will be equal to this term here. And this term is A dot, okay? Because z minus 2c corresponding to zeta minus c, right? And zeta minus c squared, okay, over zeta. And z plus 2c will be corresponding to the zeta plus c squared over zeta, okay? And here zeta and zeta is cancelled, so we have this term here. Okay, we have this relationship. And this zeta minus c will be equal to what? Zeta minus c will be equal to low 1 is potential I mu 1. And the zeta plus c will be equal to what? Zeta plus this c move to the right-hand side equation will be equal to low 2 is potential I mu 2. And square, right? This is square here. So if you compare these two, as you can see very easily, R1 over R2 is potential I theta 1 minus theta 2 will be equal to low 1 over low 2 square is potential I2 mu 1 minus mu 2 according to this term and this term. So you can simply find out R1 over R2 will be equal to low 1 over low 2 square, okay? And theta 1 minus theta 2 here will be equal to 2 times mu 1 minus mu 2, okay? So that's the relationship, okay, for the R1, R2, low 1, low 2, and theta 1, theta 2, mu 1, mu 2. So as you can see here, okay, we have a transformation, through the transformation, okay, we have this relationship, okay? And let's take a close look, okay, when I have a curve, okay, this curve across our so-called critical point here. This is the critical point in zeta plane. This is zeta equal to c here. So I have the curve, okay, originally at this point, and then it will move very slowly, and then across our critical point and move forward upward, okay, and we will see what happens when I have this small curve here. And this small curve here, okay, as you can see, is passing through the critical point. Okay, is passing through the critical point. So according to the zeta 1 here, okay, this is point zeta 1 here. Original zeta 1 is what? The angle nu 1 is what? Nu 1 is minus pi over 2, right? This is minus pi over 2. And as long as they passing through a critical point, what happens? It will change to pi over 2. Okay, because at this point here, this angle is minus pi over 2. And then when the point move to the upward in this position, and this become what? Pi over 2. Okay. That's what I mean is, okay, I have this kind of coordinates. This is our critical point. Okay, see here. And I have a curve, and this curve, this location, and you see this is a very small segment. Okay, so original when say R1 is here, I have the minus pi over 2 angle here. When I passing through the critical point here, this is become pi over 2. Okay. And according to our previous, as you can see here, okay, our angle will be double. Okay, our angle will be double. Okay, double. When depend on the new one, minus mu 2. So here, as you can see, when nu 1 jump from the minus pi over 2 here and to the positive pi over 2, okay, and nu 2 is this according to the location for this reference point. Nu 2 is what? Nu 2 is very close to 0. Originally 0 minus, right? Very slightly minus, and then across the boundary here, right? This angle becomes 0 plus. Okay. So as you can see, if you have this mu 1 change to mu 2, mu 1 change from the minus pi over 2 to pi over 2, and then theta 1 will be changed to what? We change to minus pi over 2 pi here. Okay, and so this theta 1 is this location here. Okay, and theta 1 will be in Z plane, and minus pi is here, and the pi is here. So will become what? Become so-called the cusp. Okay, so through the transformation, this is in theta plane, right? This is in theta plane. Through the transformation, okay, minus pi over 2 multiplied by 2 become pi here. So this is 2c, right? This is all. In C plane we have a so-called critical point location. So we have a minus pi here, right? Minus pi. This is minus pi. Minus pi. And then when they're passing through this critical point, what happens? Become positive pi here. So this is a positive pi here. Okay. So this is a very small angle. This is a very small angle. Okay. So it almost approach to this coordinate axis. Okay. 所以这条线其实非常接近上面这条线非常接近下来，就是这角度非常小，所以这边是 minus pi to pi. Okay. So as you can see through the transformation, when we go through this critical point, whatever, in Z plane, we will generate so-called this kind of cusp. 一个非常接的角度。Okay. Very sharp angle. Okay, so here we call this is a sharp edge, a knife edge or cusp. So this is a cusp. When you have any smooth curve passing through our critical point, and in Z plane, okay, according to the formula we just described, okay, the geometry will change to what? Will change to a knife edge or the cusp. Okay, so this is very good, okay, kind of property for us, because as you can see, through the Jacobi's transformation, we like to transform what? We like to transform a smooth curve here, right? For example, flow over a cylinder always is a smooth curve. And this smooth curve, if this smooth curve passing through our critical point, what happens? You will generate the cusp here. Okay? So this cusp will be like a trailing edge of the L4 here. So we can using this property of a mapping, okay? So our cylinder, one point will be passing through, if you want to generate the cusp or the L4 trailing edge in the Z plane, we can do that. Allow us using this flow over a cylinder, this smooth curve, passing through what? Passing through the critical point, okay? We will generate so-called cusp or the trailing edge here. Okay, that's the reason or that's the property of the Jacobi transformation. Okay, so that's, you understand this point, you can see, okay, through a smooth curve goes through the critical point, you will generate so-called cusp or trailing edge, or the knife edge, or in the airfoil will become the trailing edge. Okay, so that will give you the kind of the explanation. Okay, what happened when you have a smooth curve goes through the critical point. Okay, you will generate so-called the knife edge or the cusp at this. Okay, in the Z plane. Okay, and also this is goes through our critical point in Z plane here. Okay, so you understand this point. We can start, okay, to manipulate. Okay. Or to give you an example, okay, demonstrate the Jacobi transformation. Okay, so here is one case of a Jacobi, one example of Jacobi transformation. Okay, so here is a zeta plane. This is Z plane. Okay, and we have a cylinder. This cylinder, and this cylinder goes through the what? Goes through our two critical points, C and minus C here. So this cylinder here, we can describe this cylinder here. Zeta is equal to C times its potential I mu, right? Because C is our what? Radius, right? Radius. So this cylinder is a center, is the origin of this coordinate, and the radius is equal to C. Okay? So this is a cylinder shape in the what? In the zeta plane. So we would like to see what happens when you have the transformation go through the Jacobi transformation. So this is our Jacobi transformation mapping function. Okay, and this is our cylinder. Okay, so cylinder through the Jacobi transformation, what happened? So you plug this zeta equal to C exponential I mu here and here. So this is C times its potential I mu, and here is a C squared divided by C times its potential I mu here. So you kind of rearrange our equation here. C and C is cancelled, become C squared, and C is cancelled, become C here. Its potential I mu here becomes its potential minus I mu here. Okay, that's that. So here is, you can see here very easily, right? This is equal to what? Is equal to 2C cosine mu. Okay, 2C cosine mu. Right? What's that? Its potential I mu is what? Potential I mu is cosine mu plus I sine mu. Its potential minus I mu is what? Cosine mu minus I sine mu. Right? So if you have these two terms multiplied or summation together, these two imaginary part will be cancelled, become 2 cosine. Okay, so that's the complex variable. You should know that. Okay, so here if you this term plus this term will be equal to 2 cosine mu, and we have a C is a common factor, so it becomes 2C cosine mu here. Okay. So as you can see from this transformation, we just plug this into this transformation function and to find out what happened to Z. Z is all what? All real, right? Because Z is equal to X plus IY, right? And this is real part of Z. This is imaginary part of Z. And through a transformation for this circle here, right? This circle. And we find out in Z plane become what? Become only X real part exists. There is no imaginary part. Y is equal to 0. So if you plot this, as you can see, it becomes like this. Right? This is so through the Jacobi transformation, if I have a circle, this circle radius is equal to C. Okay, and then through the Jacobi transformation, it will be reduced to what? To a flat plate. Okay, for a flat plate. As you can see, this is a flat plate. Okay, so this is a circle in zeta plane, and through a transformation, I have this, and x equal to 2c cosine mu, y equal to 0. So it becomes a horizontal plate with a length, with a width from here to here is a 4c in z plane. Okay. Okay, so that's through the Jacobi transformation, the first example. And the second example I can show you is that if I have Okay, circular this cylinder, the radius is